Hello everyone. In this video we will solve problems chemistry AP related to acid-base equilibria. Let us start. According to Bronsted, the concept of acids and bases, a base is a proton acceptor. So base, according to Bronsted-Lowry concept, it's a proton which is H plus acceptor. It accepts the proton. According to the Bronsted concept of acids and bases, acid, on the contrary, it's a proton which is H plus, it's a proton donor. Give the conjugate acid of the following. These are substances that we need to write for them the conjugate acids. It means that we have to add for each one H plus. So when we add H plus, that turns to be HCN. Add H plus, that turns to be HS minus, and this one I want to give the conjugate base, so it means that I have to remove H plus, which turns to be H2PO4 minus. I have to remove one H plus and it turns to be an H3. Knowing that HF is a stronger acid than acetic acid, determine in which direction the following equilibrium lies. Always the equilibrium lies to the direction of the strong acid. This is stronger than this one, so that the direction, the reaction driven into completion, and it will lie to the right. At 50 degrees Celsius, the water ionization constant is 5.48 times 10 negative 14. What is the hydronium ion concentration at that temperature? Hydronium, which is H plus. The formula Kw equal H plus times OH minus. Speaking about a neutral water, when I say neutral water, it means H plus equal OH minus. I will assume H equal X. So Kw equal X squared, 5.48 times 10 negative 14 equal X squared. Radical both sides to get the value of X, which is the value of hydronium ion, and it will be up to 3 significant figures, 2.34 times 10 negative 7 molar. We add 0.535 gram of NaOH to 100 milliliter of water. What is the H3O plus hydronium ion and pH of this solution? Okay, when we add NaOH, we know that NaOH is a strong base that dissociates completely. So that will be Na plus and OH minus. Let me find, first of all, because I want the concentrations, let me find the concentration of sodium hydroxide, which is the number of mole over volume. Number of mole, it's the mass over the molar mass multiplied by the volume. The mass given to me, 0.535, the molar mass of sodium hydroxide, 40, multiplied by the volume that I have to divide by 1,000 to change into liter, that will be 0.1. Because here concentration molar, number of mole, and the volume should be in liter or decimeter cube. So the concentration will turn to be 0.134 molar up to 3 significant figures. This is the concentration of NaOH. Since it is a strong base, it means it's the same concentration of OH minus. Now I found the OH minus. Let me find the H plus. We know that Kw equal H plus times OH minus. So H plus will be equal Kw at 25, it's 1 times 10 negative 14 for water, over the concentration of the base that already we found, which is 0.134. Okay, and now which is over this one, the answer up to 3 significant figures is 7.46 times 10 negative 14 pH. A molar. Now pH equal negative log H plus. I substitute 7.46 and the answer up to 3 significant figures will be 13 up to 4 significant figures for 13.12. So this will be the answer for question number 8. OH minus, it will be 0.134. H plus is 7.46 times 10 negative 14, and pH is 13.12. Move to number 9. We have a 4.63 times 10 negative 4 molar solution of HCl. What is the pH, pOH, H plus, and OH minus of this solution? We know that HCl is a strong acid that dissociates completely into its corresponding ions, H plus and Cl minus. So if this is 4.63 times 10 negative 4, it corresponds that the concentration of H plus is 4.63 times 10 negative 4. So we found H plus, which is 4.63 times 10 negative 4 molar. Now let us find OH minus. OH minus is equal to Kw over the concentration of K plus. He didn't mention any temperature. I will assume it at room temperature. So Kw for water at room temperature, 1 times 10 negative 14 over 4.63 times 10 negative 4. And the concentration of OH minus up to 3 significant figures, it will be 2.16 times 10 negative 11. Now let us find the pH. pH is negative log H plus, which is 4.63 times 10 negative 4, and the pH answer is 3.33 up to 3 significant figure. We know that pOH plus pH equal 14, which means that pOH is 14 minus 3.33, and the answer will be 10.7. Number 10, for the following reaction, give the acid, base, conjugate acid, and conjugate base. If we have to have a close look to the equation, we see that H2PO4 minus turned to H3PO4. It means that according to Bronsted and Lori, it gained H plus. It gained H plus, which made this a base. And the water acts as an acid. So this will be the conjugate acid of the base, which is H2PO4, and that will be the conjugate base of H2O. What is the pH, pOH, H plus, and OH minus of 0.350 molar solution of acetic acid? Acetic acid is a weak acid, which means that it dissociates reversibly. So CHCOO3 minus, it dissociates reversibly because it is a weak acid. I construct for it the equilibrium table: initial, change by reaction, and equilibrium. So I stands for initial, I will use concentration. C stands change by reaction, and E is the equilibrium state. The concentration of acetic acid given to us at the beginning is 0.350. I will assume this 0. H plus, it's 10, there is H plus from water, but it's 10 negative 7, which is very small. I will assume it to be 0. Change by reaction minus X, X and X, and that will be 0.350 minus X, X and X. At equilibrium, we can write the equilibrium constant expression. Ka equals CH3COO minus times H plus over the concentration of the acetic acid, which is X times X, X squared over 0.350 minus X. And the value of Ka is given to me, which is 1.8 times 10 negative 5. Since the value of Ka is very small, we can neglect this and we can solve for X. After I do the calculation, X squared equal 6.3 times 10 negative 6. Now radical the answer to solve for X, which is the value of H plus, and it will be 2.5 times 10 negative 3 molar. Let us find the concentration of OH minus. I'm assuming 25 degree. It means KW 1 times 10 negative 14 over the value of H plus, which is 2.5 times 10 negative 3, and the answer will be 4 times 10 negative 12. To find pH, it's minus log H plus, which is negative log 2.5 times 10 negative 3, and it's equal to 2.60. To find the pOH, it's simply 14 minus pH, which means 14 minus 2.60, and the value for pOH is 11.4. Now let us move to number 12. A 0.1 molar solution of chloroacetic acid has a pH of 1.95. What is the ionization constant Ka for this acid? Speaking about ionization constants, so since we want to calculate, so it's a weak acid, because for strong acids Ka just is very large. So let me constitute table and equilibrium table for the following equilibrium. So chloroacetic acid is a weak acid that dissociates reversibly to give its corresponding ions, and ICE, the initial in molar, which is 0.1. This is 0. I will assume H plus approximately 0, minus X, X, and X. So at equilibrium, 0.10 minus X, X, and X. Now I can write value for Ka, but before there is a given that I can get the benefit from it, which is pH equal 1.95. So it means that H plus is 10 negative pH, which is 10 negative 1.95, which is equal to 0.0112 molar. Like this, I found the H plus that corresponds to the value of X at equilibrium. Now, at equilibrium, constant of acidity is the concentration of Cl H2COO minus times H plus, all divided by concentration of ClCH2COOH, which is X squared over 0.10 minus X. X already I found it, so we substitute 0.0112 all to power of 2 over 0.10 minus 0.0112, and the value after calculation for Ka, it will be 1.4 times 10 negative 3. In such a case, I never neglect X, because I don't know the value of Ka, whether it's small or big. If I know the value of Ka and I need to find something else, then I do the neglection for the ease of calculation. About this time, you may be wishing you had an aspirin. Aspirin is an organic acid with a Ka value of 3.27 times 10 negative 4, and he gave me the equilibrium table, the equilibrium equation. If you have 2 tablets, each containing 0.325 of aspirin mixed with a neutral binder to hold the tablet together, and dissolve them in a glass of water of volume 200 milli, what is the pH of the solution? Because this aspirin is a weak substance, it dissociates reversibly, and usually we use the initial concentration. Let me find the concentration. I have the mass. Let me find first of all the number of moles, which is the mass over the molar mass. Because 2 tablets and each is 0.325, so I multiply 2 by 0.325, divide by the molar mass of aspirin, which is 180. The answer is 3.61 up to 3 significant figures times 10 negative 3 molar. I found the number of moles, so I can find the concentration, which is the number of mole over volume, which is 3.61 times 10 negative 3. Volume definitely should be in liters, so I divide 200 over 1000 to be 0.2, and the answer is 0.018 molar up to 2 significant figures. Now I found the concentration. I can construct equilibrium table from the equation HC9 H7O4 plus water, this is aqueous liquid, to give me the corresponding ions C9 H7O4 minus and H3O plus, and let us construct the table and substitute ICE. The initial concentration already I calculated, 0.018. For liquid there is no concentration, so dash, this is 0. Change by reaction, this will be minus x, x and x. Equilibrium, it's the summation of the above two steps, 0.018 minus x, x and x. Like this I can be be able to calculate x from the taking the equilibrium stage and writing the equilibrium constant, which is x squared over 0.018. Ka given to us 3.27 times 10 negative 4, which is x squared over 0.018 minus x. Here we can neglect for the ease of calculation based on the fact that Ka is small. So after I calculate and radical the answer, x, which is the concentration of H plus, it's 2.43 times 10 negative 3 molar up to 3 significant figures. Now to find the value of pH that he wants, it's negative log H plus, which is negative log 2.43 times 10 negative 3, and the pH value is 2.62. Show how the following acids and bases would react in water. So if I add to HF liquid, if I add to it H2O liquid, according to Bronsted-Lowry, HF is the acid, so according to Bronsted-Lowry it will migrate from HF to water, so I am left with F minus and H3O plus aqueous. Ammonia, which is gas, or I can take it in the aqueous form, plus water. Ammonia is a base, so H plus will be directed from H2O to ammonia to give us an H, according to Bronsted and Lowry, an H4 plus and OH minus aqueous. HNO2 nitrous acid, which is a weak acid, but it's acid, so H plus according to Bronsted and Lowry will be directed from HNO2 to water, and I will be left with NO2 minus, and that will be H3O plus. Acetic acid is a weak acid, so but still acid, so H plus will migrate from acetic acid to water, and we will be left with the acetate ion plus H3O plus. Number 15, you are given 0.1 molar aqueous solution of the following compounds. In each case, tell whether the solution will have a pH equal to 7, less or greater than 7. This is phosphoric acid. It is a weak acid, so pH less than 7. This is salt, which is acidic salt. How can I tell? I can tell from the presence of highly charged metal, which is Al3+. Highly charged metals, they are acidic, they form acidic salt, so the solution has a pH less than 7. K2CO3, this is a salt that came from KOH, a strong base, and carbonic acid, a weak acid. The salt follows the nature of the strong parents. The strong parent is base, so this is a basic salt, which makes pH greater than 7. KNO3 also, it's a salt that came from KOH, which is a strong base, and nitric acid, a strong acid. Both of them, they are strong, so the pH, so it's a neutral salt. It's a neutral salt, and the pH equal to 7. Now show how the following salts would hydrolyze in water. I have KF. This salt, KF, in water, it gives the corresponding ions, K plus and F minus. Now, between these two ions, only F minus has affinity to water. Why? Because a K plus, it comes from KOH, which is a strong base. Its ion has no affinity to water. While F minus comes from weak acid HF, which is a weak acid. Its ion has affinity to water. So F minus only has affinity to water. If I put it in water, according to Bronsted and L'Oreal, H plus will be captured by F minus, and it will be giving me HF plus the remain OH minus. Now NHBr also, I have NHBr salt. If I add to it water, it gives the corresponding ions, NH4 plus and Br minus. Br minus has no affinity to water. It's coming from hydrobromic acid, which is a strong acid, while this comes from ammonium hydroxide, which is a weak base, so this has affinity to water. So this ion, NH4 plus, I add to it water, and according to Bronsted and L'Oreal, H plus migrate from NH4 plus to water to be left with NH3 aqueous and H3O plus aqueous. Now NaNO2, again this is a salt. If I add to it water, it will split completely to the corresponding Na plus and NO2 minus. Na plus coming from a strong base, no affinity to water. NO2 minus coming from nitrous acid, which is a weak acid, so the ion has affinity to water. So NO2 minus in hydrolyze plus water. According to Bronsted and L'Oreal, H plus migrate from water to NO2 minus to give the corresponding HNO2 aqueous plus OH minus aqueous. Now lithium acetate, also it's a salt. In the presence of water, it gives the corresponding ions, lithium plus acetate ion. Lithium comes from base LiOH, which is a strong base, so its ion has no affinity to water, while acetate comes from a weak acid, acetic acid, so it has affinity to water. So CH3COO minus plus water, and according to Bronsted and L'Oreal, H plus migrates from water to the acetate ion to give the corresponding acetic acid plus OH minus. The last problem, what is the OH minus and the pH of 0.1 molar solution of sodium cyanide, and it's given to me the Ka of hydrocyanic acid. First of all, sodium cyanide, it's a salt. In the presence of water, it gives the corresponding Na plus and OH minus. Na plus comes, and Cn minus. There is no OH minus here. Okay, and Cn minus. Na plus comes from a strong base, NaOH, so the ion has no affinity to water, while Cn minus comes from hydrocyanic acid, which is a weak acid, so it has affinity to water. So I can construct equilibrium equation with the equilibrium table, Cn minus plus water, to give, according to Bronsted and L'Oreal, H plus migrates from water to Cn minus to give the corresponding HCN plus OH minus. Now I can construct the table ICE. The concentration initial, if this is 0.1 molar, so Cn minus 0.1, the ratio is 1 to 1. So this is 0.1 molar. No concentration for liquid. This is 0. OH minus, I will assume it's 0. change by reaction, minus x, x and x, 0.10 minus x, x and x. So at equilibrium, I can write the KB. Pay attention, it's not Ka, it's KB. Why? Because here there is liberation of OH minus, indicating that NaCN is a basic salt. How to find Kb from Ka? We know that Ka times Kb equal 10 negative 14. So like this we can find the value of Kb, which is 10 negative 14 over 4 times 10 negative 10. So the value of Kb is 2.5 times 10 negative 5. And the expression for Kb is x squared over 0.1 minus x equal 2.5 times 10 negative 5 times 10. Okay, no problem. Okay, I will write it on another line. So I will rewrite Kb, which is 2.5 times 10 negative 5 equal x squared over 0.1 minus x. Because the Kb is very small, so this will be neglected. So I do the cross multiplication and radical the answer, and x, which is the value of OH minus, it is 1.58 times 10 negative 3 molar. Like this, I will be able to find the POH, which is negative log OH minus. So negative log 1.58 times 10 negative 3, and the value for POH after calculation, it's 2.80. But the question looking for value of 8 pH, so no problem, there is relation between POH and H. So we say but pH plus POH equal 14. So pH equal 14 minus 2.8, which is equal to 11.